Alrighty then. Good evening, everybody. I'm Henry from 314 Education. Today we're going to be trying a new thing. I want to see if we can get enough pieces in place that we can start looking at AP physics problems and solving them live via a live stream. And so, yeah, want to just, this is going to be kind of a test of the technology for this first stream here. So I appreciate your patience, and I'm going to be having to jump between a few different windows here. But primarily we'll be looking in this upper right side. Sorry, I'm mirror image to you guys. Over here is our problems. Below us is where we have some scratch work, and then down in the corner there is a calculator. And so this should kind of be a little workspace for how we can tackle our AP problems here. So that being said, let's just jump right into it. So our first few questions are looking at these two graphs. We're comparing object A with object B. We've got two graphs here. One of them starts traveling at 1 meter per second and then goes down to a negative 1 meter per second after the first second. But the second object starts at a very slow speed and travels steadily up to 1 meter per second by 2 seconds. It looks like we've got some sort of quadratic growth there. But we want to find out which object is farthest away from the origin at t equals 2 seconds. And to tackle something like this, we can use the relationship between velocity and position when we're dealing with a graph. If we have a velocity time graph, the area under the curve is going to give us our position. And so in this first case, we have an area of, let's see, the time was 1 second, and this was like a +1 meter per second. But then we also have a negative square with the same size, because it's got the same height, only it's a negative 1 meter per second instead of a positive 1 meter per second. And it goes from 1 second to 2 seconds, so it still has the same width. So we actually expect our x displacement for this to equal 0 at time equals 2. As for our second one, though, we're dealing with a kind of a quadratic type thing here, where this is just growing up at an increasing rate. Granted, that wasn't the best drawing of it. Let's see if we can get that a little bit more obvious. There we go. Oops. And so if we draw down here, we can see that's at our time at 2 seconds, and we still reach this +1 by the time we hit 2 seconds. So our area under the curve is just going to be this guy. And so we can work this out mathematically if we had the function. We actually don't need to, because all we need to know is that x is a positive value, is some positive value greater than 0. And so that's all we need for the context of our question here, because our question asks us which object is farthest away from the origin. And so that's going to be the object with the positive displacement. So that would be B. And so we're going to try using the little circle highlights in Adobe for marking our answers here. Which object moves with constant non-zero acceleration? Okay, so bringing back over to our graphs here, our acceleration relation is going to be, let's change colors here. Acceleration is going to be the rate of change of velocity with respect to time. And so the rate of change with respect to time when we're graphing velocity versus time is going to be the slope. And so if we look here, we have a slope of 0 at the top here and a slope of 0 at the bottom, and then an infinitely negative slope as we drop down in that instantaneous jump there. But if we look at our other guy here, we see that our slope is going to be steadily increasing, right? We have a positive slope there, and then an even more positive slope here. If we were to draw a line tangent to our curve here. And so some of you might have seen some calculus, would recognize that would be a derivative although this is technically a non-calculus level course, so we don't need to do the calculus, but we can just see the acceleration. Let's see, so they want a constant though. So we have non-zero acceleration for B. Constant, we actually don't expect this to be constant, because a constant case would be something that looks like something like that, right? A constant slope. This slope is not constant. And so, yeah, so we're actually, our best answer here is now D, because this doesn't fit for our first object nor our second one. So neither A nor B is our answer for this guy. And then 3 asks us about the object returning to its initial position after t equals 2 seconds. And so that's going to kind of come back to what we talked about originally. This is going to be the first one because we have as much area under the curve in the first second as we do in the second second. As we look at 2 seconds here for our second one, this is still not, still not a negative term to bring it down. So that takes us away from its initial position, but A does go to its initial position. Also, those seem to be jumping to the left. I'll try and make a conscious effort to click more to the right. How are we doing? We got, okay, the stream is running live, looking good. Still just checking the tech as we go. So, again, thank you for your patience. Okay, so 4s, that's we're looking at a new graph now. We've got velocity versus time for an object moving in a straight line. And we want to know what time after t equals 0 does this object return through its initial position. And so to take a look at that, we want to break this up into, let's get a quick drawing here. So we had, there's a negative little triangle, a positive piece, a flat piece. Okay, this is, I need to be drawing this on a flat surface. Let's try that one more time. Okay, that's slightly better. So we're going up and over and then down, and that should be further along. This is our V, this is our T. Let's see. And so for our first one, our negative area under the curve is after 1 second, and we have a height of -1, that would be meters per second. So we want to find out, so we, at the beginning, after the first second, we've displaced ourselves by this area. And so at some point between here and over here, we reach an area that is going to be equal in magnitude to this first area. And when that time, whatever that time value is for our x-coordinate, that's going to tell us the time that we return to our original position, because we'll have 2 areas under the curve that will cancel each other out. So to do this, this first bottom one, we want area of this triangle is going to be 1/2 base times height, bh over 2, which in our case is -1 times 1, so we get a -1 over 2, -1/2. And so now we're looking for the case where we have a positive area of 1/2. Looking back at our problem, we're going from 1 to 2 in 1 second. That is what we have going on here, down on this guy. So this would be a height of 2. This is 2 seconds, so this is a gap of 1 second. And so the area of this short triangle here is then going to be double what we want, because that would be base times height. Our height is 2, our base is 1, and we divide this by 2, we're going to get an area of 1. And so we don't want that, we want an area of 1/2. And so for the time to equal 1/2, that's going to be our base, right? So our if we have our height, let's see, how do we want to do this? height, so our height is going to be 2t. And then we're gonna so based on from if we look at this from 0 to 1 instead of 1 to 2, our height is going to be as a function of t rising with a slope of 2. And then our base is going to also be this t, because that's our distance across, and then that's all over 2. And we want this area to equal 1/2. So that means then we can multiply this by 2. We get 2t squared is equal to 1. So we have t squared is equal to 1/2. And so that leaves us then with our time being 1 over the square root of 2. And we have to be careful too, because this was for the case that we decided where we're looking at 0 to 1 for time. And so we're really adding on a second. So our actual time is going to be 1 plus 1 over the square root of 2 seconds. And there might be a better way of expressing that. Let's take a look at our options. It is really just between 1 and 2. Okay, so this is a good example of reading your options fully. We could have saved us a little bit of time. But that's okay. I mean, we still took the time to calculate a good answer. On the actual test, you would be working with a time limit. We're not going to be doing that for today, though. This is just to take a look at the problems and the different approaches we can use. Cool. So let's take a look at our next guy. Let's get a new page here. Oh, I double-clicked that. We don't need that many. Well, we probably will, but we'll save the other ones for later. Okay, so we've got a body moving in the x positive direction passes the origin at time t equals 0. Between t equals 0 and t equals 1, the body has a constant speed of 24 meters per second. At t equals 1 second, the body is given a constant acceleration of 6 meters per second and 6 meters per second squared in the negative x direction. And so we want to find the position of the body at 11 seconds. Okay, so let's do, so when we want to find a position with changing velocities and whatnot, we write our position as a function of time. And so we're going to add up all of our little components. We're going to start with a quadratic component. This is going to be for our acceleration. And I call it quadratic because it's got this little t squared in here. And as we see, we'll be able to get this whole equation as a quadratic formula, although we probably won't need to do that for this case. But that's something you can always have in your back pocket, just in case there's no way to factor it out and it just gets way too complicated. Our linear term would be our velocity, our initial velocity in the x direction, right? That's what we were given to start with. This is our acceleration. And then we'll have any initial x displacement. And so all of these pieces added together shall give me my total position. And so let's take a quick look again. What did we have? Between t0 and t1, the body has a constant speed of 24 meters per second. So that's where we're starting. We're starting that velocity. And that's also going to be our initial displacement. So for our specific case now, they said our acceleration was in the negative direction, right? So that is -6 times t squared. Yeah, that's okay. I say we got to be a little bit careful because of that didn't start until 1 second in, but that accounts for this. It should account for this, hopefully. But we've got a positive 24t, and then we had 24 meters for that first second before the acceleration kicked in. So that's going to be accounted for here. And so we want to find out at t equals 11. And so what we'll do is we'll plug these in. T squared, 11 squared is 121. Then we'll have 24 times 11 plus 24. And so this is kind of a calculator level problem, I think. So we'll have 121 times, I want a -6. Oh, it doesn't. 6 negative. There we go. Is that gonna? Oh, that did it horribly, didn't it? Okay, so 121 times. I want. How do I get it to be just negative? So that's this guy. And there's no key for it, so I have to click it. -6 divided by 2. And then we'll add on, we want 24 times 11. 24 times 11. And then we'll add on 1 extra 24 for that first initial displacement. Okay. And strangely enough, we don't get one of those options. So let's have a look, see where we've made a mistake. So I'm a little bit skeeved out at this step because this doesn't jump in until our time's already going. And so I think this is going to skew this more negative than it needs to be. So just as an instinct, I think that it's probably going to be this -36. But let's see if we can prove that then. So this would be, if we weren't counting from 0 to 11, we'd be counting from 0 to 10. If 0 to 1 didn't count, and this will account for that 0 to 1 time. So let's look for it when t equals 10. So this goes to, let's actually just clear those. Here we go. Can I make that bigger? I think there was like a slider for it, wasn't there? Maybe not. That's fine. So let's change that to 100. Let's change that to 10. So this would be 100, and then this would be 10. Let's try calculating that again, but with our revised values now. So we'll take 100 times -6. So let's click on that there. Divided by 2. Plus 24 times 10, which is 240. And then plus that last little 24. And so that's going to give us that -36. Okay. That is equal to -36, which should be our final position. So that is C. And notice how we were able to kind of predict that a little bit anyway, because we were close with the 99, but we had a little bit of a throw off by the acceleration not starting until 1 second in. Good. So now we're taking a look at, we've got a diver moving horizontally with a speed v, dives off the edge of a vertical cliff, lands in the water at distance d from the base of the cliff. How far from the base of the cliff would the diver have landed if the distance had been, if he had been moving horizontally with a speed of 2v? So in these cases, where we've got some sort of like a falling object, and so we're measuring some sort of projectile. Let's draw our little guy in here. Yay, there he is. And so he's got some initial velocity v, and he's gonna kind of jump and follow a little trajectory and land some distance d from where he started, right? And so this d comes from this same relationship we had up here. When we break up our kinematics into 2 dimensions, we have an x dimension and the y dimension, right? And so in the x, we have no acceleration and we'll have no initial displacement. All we have is our initial velocity. This is just going to be v times t. Velocity times time is our distance, which, yeah, I guess in this case is a d. Our y though is gonna have an acceleration, which is g, and then we have the initial height of the cliff. And so this would be the case that we would want to solve for to get the time from. Notice, however, though, that none of these depend on the velocity, right? because we have no initial y velocity. He's moving horizontally. So if we increase the v to 2v, this just doubles this. This doesn't affect t at all. And so our distance then similarly is just getting multiplied by 2. And so in this case then that would be a case of, can I do this with pen? I can, yeah, that's good. It would just be this 2D answer there. Cool. Oh, that's too many. There we go. Awesome. Okay, so now we're looking at a projectile fired with an initial velocity, v naught, at an angle theta naught, with the horizontal, and it follows a trajectory shown above. Do we have a trajectory shown above? Not really. There's a trajectory shown here. This is probably what it meant. Or we're missing a piece. That's okay. We'll assume it's an object being fired in a parabola. Which of the following best represents the vertical components of the velocity and acceleration, respectively? Okay, so we've got little pairs of graphs here. So let's see what we've got here, and we're looking at the vertical components. Oh, that isn't at an angle. Let's try this. Wow, it's strange that I had to rotate myself to get that flat, but it kind of worked. Okay, now I'm not able to draw. I don't know what's going on here. There we go. So we're launching with some initial velocity v0 at some angle theta 0 above. We're experiencing a constant downwards acceleration due to gravity. So we expect a negative 9.8 meters per second as a constant for our acceleration. So looking at our choices, that means we can already rule out A, B, and C. Okay, so I guess that does leave us with D here. But just taking a look at what this velocity curve is, that would actually be what we would expect, because our velocity starts out positive, decreases at a linear rate, that linear rate being g, and then we cross into some critical point here where we cross 0 and then go into the negative. And that critical point on our graph would be the top here, right? At some point, we run out of upwards velocity and start going back down, right? And that's when our acceleration has overcome all of that initial velocity and is bringing us back down towards ground. We could calculate that if we had v naught and theta naught. That would be, we could break this up into a triangle, and that would be the y component of this triangle when that gets supplanted, I guess, by this acceleration term, is how high we would get. Good, but yeah, that's that one we were able to solve for just using test-taking skills, because we could rule out all the first 3 options based on the acceleration curve, or the acceleration graph. Cool, so moving on to questions 8 and 9, we've got a ball thrown a parabolic path above, similar to what we had before. Negligible air friction, point Q is the highest point, P and R same height. Okay, so P and R are the same height compared to each other. So how do the speeds of the ball compared to the 3 points compare? And so as we're traveling upwards, we've got a lot of initial speed, but we're being slowed down by acceleration. And so VQ is going to be our lowest point, right? So immediately we can rule out A and B, because we expect our slowest velocity to be at Q. And so P and R doesn't make sense for that to be at the bottom, so those two are mistaken. But the difference between C and D is how it compares R and P. And R and P are at the same height, and so if we were to solve this with conservation of energy, we would know that the potential energy we've lost would be converted into the same amount of kinetic energy, which corresponds to mv squared, which means it would be the same velocity. Another way of looking at this from the kinematic perspective would be each one would have equal time either side of the minimum to be influenced by acceleration, right? This still has the initial velocity at p and is being decelerated for the same amount of time as it is then being accelerated from that 0 point back to that original point. And so we would expect them to have the same velocity. I personally prefer the conservation of energy method a little bit more myself, just because I've worked with energy a little bit more extensively, so that feels a bit more natural for me. But whatever makes more sense to you should be the method you should use to approach these problems. Cool. So now, next we're asked, which of the following diagrams best shows the direction of the acceleration of the ball at point P? So yeah, kind of a trick question because it doesn't matter our point, right? Air friction is negligible, so there's no other force acting on us other than gravity. And gravity is going to be our only accelerator, and it's going to be pointing downwards. So that is D. 10, we've got a nice graph here. Graph above represents position versus time for an object being acted on by a constant force. The average speed during the interval between 1 and 2 seconds. So our average speed is going to be the rate of change, right? We can call it the slope, we call it the derivative if you want to do calculus, but it's basically going to be the amount of, the kind of rise over run here. And so if we look at 1 second, we're kind of at about 2 meters, right? And then we cross the 2-second mark, we're at about 8 meters. So we basically travel 6 meters in 1 second. So that unit would be 6 meters per second for our velocity. Cool. How are we doing? Just checking on the stream, making sure we've got everything going here. Yeah, if you have any questions in the chat, please feel free to ask. Yeah, I think we'll just keep on going here. Let's see. Next we've got, we're comparing 2 cars. One of them is going to be accelerating, and one of them is moving at a constant velocity. We can tell from this curve is a velocity time curve graph. At time equals 0, car X is traveling with speed v0, yep, and car Y is just starting to move, starts at 0 and speeds up. They then travel 2 parallel lanes the same straight road. Graphs of speed versus time for both cars shown above. Which of the following is true at time equals 20? So these are going to be at the same velocity. It doesn't mean that they are passing, because car Y, the area under the curve, is smaller than the area under the curve for X. So it's not going to be passing. Car Y is going to be behind X. I say D. I was thrown off by that because D also looked like an attractive option because I misread it. I thought, well, car Y is accelerating faster than car X because this has got a steeper slope than this. But that's not what D is saying. D is saying car X is accelerating faster than car Y. And that's not going to be our case here. We're expecting car Y to be accelerating faster than car X. So that D is also not true. So we do still expect car Y to be behind car X. And that's just because the area under the curve up to the time 20 is smaller than the area under the curve for car Y up to time 20. From time t equals 0 to time t equals 40, the areas under both curves are equal. Therefore, which of the following is true at time t equals 40 seconds? So if they're equal, they've reached the same position, and so that would be car Y is passing car X, because car Y is traveling then at a higher velocity. So if they reach the same position, one's moving at a higher velocity, that means that car is passing that car. Which of the following pairs of graphs shows the distance traveled versus time and the speed versus time for an object uniformly accelerated from rest? So uniform acceleration means that our acceleration is going to be a constant value. So that means we can tell right away from our speed we expect a constant slope. So we can rule out B and C here because these have our speed slopes are curved here. And so A and D look good. And so the only difference now is how they treat the distance. And we can see our distance on A is we start covering a lot of ground very quickly, but then we slow down. That's not really what we expect to be happening. As we go faster and faster, we expect to be covering more and more ground each second. And that's sort of what we see on, that is what we see on D. See how these steps in the beginning are really kind of negligible until we get further on, and then we start making massive strides with each little step we take. So D is going to be our option here, just because that will tell us, yeah, that gives us the best representation of both the distance and the speed we want. Cool. So 14 looks like we've got a pair of vectors, equal magnitudes at times t1 and t2 respectively. Okay, so we're kind of rotating upwards. The average acceleration of the object between t1 and t2 was, so our acceleration is the rate of change of velocity. We have to be a little bit careful though, because our velocity has both magnitude and direction. It is a vector quantity. And so that means, let's actually draw this one out here. So let's see, we've got our first case. Let's see, do they have this as like north, south, east? I don't remember. They do. Okay, so these are compass points. So north, south, east, west. We have two cases. I'm going to draw them on the same curve here. But our first one is kind of pointing off this way. And then we're moving to a position where we're pointing up this way. And so our first instinct might be, oh, well, we're going to be accelerating upwards because that's where our vector's going. But if we were going to be accelerating upward, we would have a component that is still in the same direction as this guy, right? So if I were to draw an upwards acceleration, I could compare that to this component, and we'd see that this bottom line here is in the same direction as our velocity vector. And so that means if we accelerated upward, we would be stretching this vector, meaning that our velocity vectors would not have the same magnitude, which is one of the stipulations we set here. So that can't be the case. So really, the only way for this to work then would be if we have a case, let's clear this out, is if we have a case where we are moving totally perpendicular to our original vector. This is just going to rotate it without actually stretching it or shrinking it. One of the conditions we want to satisfy. And so if we displace this vector down to the origin to see where it's pointing, it's north of west, kind of in a northwest angle here. And so that would be D, north of west. Yeah, and so that's just because we need to conserve the length of the vector. And that's because of this first sentence, they are shown to have equal magnitudes. Cool, so the velocity of a projectile launch has a horizontal component, VH, initial launch velocity, and a vertical component, horizontal component, H, vertical component, VV. Air resistance negligible, projectiles at its highest point of trajectory when which of the following shows vertical components and horizontal components of its acceleration. So our acceleration isn't going to change the whole time. We still expect for every time in this projectile's trajectory that its acceleration will be g. It's under constant acceleration due to gravity, pulling it downwards. So immediately we can rule out a and b. We know that we want something ending in a g. And also our horizontal velocity is also not going to change because we were told air resistance is negligible. Air resistance would be the only force that can actually slow us down horizontally in flight. Without that, there's actually nothing opposing it, so we will have a constant horizontal trajectory. And then also we can see for the highest point of its trajectory, the highest point is the last bit of vertical velocity we have before the downwards acceleration overcomes this. And so that last moment is when our vertical velocity is 0. So this case would be D. There we go. And we could have got that a little bit earlier from our test-taking skills, knowing that we had to have these two components, and this was the only option with those two components. But we checked to make sure this first component was right also, just to be sure. So for 16, we've got a graph above, shows velocity as a function of time for an object moving in a straight line. Which one would have the displacement as a function of time for the same interval? So let's draw this one out. I kind of like that. Can we fit this here? I bet we can. We've got a velocity curve I keep calling them curves. I mean, yeah, it is a velocity curve. I call it a curve. That doesn't mean that it has to actually be curvy. It can be made with straight lines. This is just I guess you'd call it a notation thing. But so we've got some points here, and so basically what's happening is in this middle region, our velocity is constant. So we expect our x curve, this one will actually be curvy, in this region here, the same time region, we expect this to be moving linearly at a linear constant velocity. But we still have a total area under the curve for these other parts, right? And so we're still moving in the positive x direction. As this first one, though, we're moving at an increasing rate, right? So we have our rate of change of velocity is constant, but that is our rate of change of x is increasing. So x is increasing at an increasing rate. That's going to look something like this, like a little quadratic. And they don't quite line up, but we're just going to draw each kind of artifact separately, and then we'll compare it to our picture. And then this has the opposite case. Our rate of change is decreasing. We're starting with a higher positive velocity and going to a lower positive velocity until we reach 0. That's going to be the case of kind of that inverse quadratic. We're just kind of evening it out. And so drawing this whole thing in a nice clean version, let's draw it in red. We've got this kind of upwards curve, flat part, and then curve it back. That looks most like D. D has the same features we want, where it's still got that middle flat part. There's decreasing at the top and there's increasing at the bottom. So D is going to be our best option for this. Cool. A target T lies flat on the ground 3 meters from the side of a building that is 10 meters tall. Student rolls a ball off the horizontal roof of the building in the direction of the target. So we're traveling in a horizontal trajectory again. We've got no y components to our launch. Air resistance is negligible. Horizontal speed that the ball must leave the roof if it is to strike the target is most nearly. So that means we want to set our initial velocity. Let's look back at this case here, because this is very similar, right? We had our x component was equal to our velocity component times time. And then the time comes from this part here. And so solving for this, we want to know the time at which our y equals 0. And so I'm going to have 0 equal 1/2 gt squared plus h. And I want to solve for what that time is. And so let's take t squared is equal to, we're going to pull a negative h over 2 over g. There we go. And we take the square root. And I know everyone's panicking now because I'm taking the square root of a negative. That doesn't make any sense. You can't do that. Well, you can if you use imaginary numbers, but we're not doing that here. There's actually a sneaky little trick here because this g embedded is a negative number. We define this as a positive acceleration, but we know this is going downwards. So that means the g takes on the negative. So this is a negative 9.8. Which, if we're making an approximation, we'll probably use negative 10. And so we'll have this be negative 2 times our h, which was 10 meters? 10 meters. 10 meters over our g, which we'll approximate as a negative 10 meters per second squared. And that now we see the negatives cancel. We're actually not dividing by a negative, we're not taking the square root of a negative value, which is good because I don't want to use imaginary numbers. Actually, I do. They're good fun, but we won't do those for today. So I expect this to land in a time of √2 seconds. And so what I need to do now is I've set my time. I want to find my velocity, which is just going to be my x over t. And the x that I want to fix that x is going to be the distance from the side of the building to the target that we're traveling. And so that was 3 meters. So we expect our velocity to be 3 meters over √2 seconds, or 3 over √2 meters per second, which is C. Awesome. How are we doing on this, by the way? It's there. This is, I know this is like a massive document. Oh God. Yeah, I don't think we're gonna do all of this. We're not gonna do all of this today for sure. Let's see. We'll do some more though. So we've got graph above shows velocity versus time for object in linear motion. Which of the following is a possible graph for the x versus time? So again, we're just moving between different graphs, right? Moving between velocity and x in this case. So for our first case, we have a positive constant velocity. So we expect a constant rate of change. We are changing directions and going down. We cross over 0, so that means our x is changing directions at around here. And then we're going back down to another flat part where it's constant. And so the graph that has all of those features would be A. We have this positive increase accounts for this positive part up here. This curvy change in directions is demonstrated by this change there. And then this comes back down to another consistent downward slope, which would be this flat part here. Good. So we've got a student testing the kinematic equations for a uniformly accelerated motion by measuring the time it takes for a lightweight plastic balls to fall to the floor at a height of 3 meters in the lab. Student predicts the time to fall using g as 9.8, but they find the measured time to be 35% greater. Which most likely causes the percent error? Acceleration of gravity does depend on your location a little bit, because the gravity we experience is also subject to the Coriolis force, which is going to be a function of your latitude, because that is due to the rotation of the Earth. That wouldn't account for 70%, a big 35% error. That's not reasonable. This is way too high of a value. More likely, though, our kinematics are not accounting for air resistance, which would be C. Especially with lightweight plastic balls, you'll notice that if you ever do an experiment with ping pong balls, air resistance comes into play very quickly, because their surface area to mass ratio is very high, and that is very useful for something with strong air resistance. If you think of something like a parachute, that covers a massive surface area, but doesn't have a lot of mass, so it traps a lot of air. That's how we're able to fall safely. But again, that is something that would mess up your calculations if you were ignoring air resistance. Okay, so now we've got an object thrown from a cliff, again, neglecting air resistance, but we've got an angle, we've got a velocity, and we've got a height. So we've got kind of our full scale complexity for our projectiles as we can go. And so, but this is just going to be a qualitative one here. And so when we launch this, we want to find, right before we hit the ground, the angle with the horizontal. We want to compare that to our original theta. Are we given an original theta? In order for the object to travel a maximum horizontal distance. Oh, okay. Sorry, I was confusing that. So, so for maximum distance is going to be, I mean, it optimizes to 45 degrees. That's not one of the options, is it? Maximum horizontal distance. Well, so the maximum horizontal distance would give us, we can get a little bit further than just the 45 degrees if we started at this initial height, right? So I'm comparing B and C as our two front runner options, because both are right in that ballpark, right around that optimal angle, 45 degrees. This is greater than 45, but to 60. This is between 0 and 45. I actually like the 0 and 45 option better, though, because of this initial height. And that's because we're going to get a little bit more x component. And so as our time from us falling in the y direction is going to be added onto a little bit by this extra h, we're going to enjoy a little bit more x displacement, because our x component of our velocity is going to be higher if we take the slightly less steep angle. That would be greater than 0, but less than 45 degrees above the horizontal. And we don't want the case of it below the horizontal because that's just throwing it straight down. Well, not straight down, but angling it down towards the ground much too quickly. We still want the nice full arc trajectory. Okay, next we've got starting from rest at time t equals 0. Car moves in a straight line with an acceleration given by the accompanying graph. What is the speed of the car at t equals 3 seconds? We've got our acceleration. So once again, this is just going to be an area under the curve type thing. Oh, I didn't want that. So we've got a triangle of 2, and let's get our Jamboard. So things I'm learning right away. This Jamboard would be a good thing to keep visible where I can still see the problem. Because now I'm in a position where I have to draw this from memory. I know you guys can see the problem on the stream. And so that's something I can work out on my own time. But so, similarly to how we related velocity to position by area under the curve, the same goes in relating acceleration to velocity. Velocity is the integral of area, of acceleration, which is the area under the curve. And so we were looking at some time down here. What do the problems say? Let's just jump back. It was at 3 seconds, and we're starting at 5. Okay. So this is at 5. This is 3 seconds. So this drawing is not quite to scale then. But so here we've got a triangle where the area 1/2 base times height, which is going to be equal to, if we're starting above, this is like where 2 is. And then this is just going to be 2 times 3. So this is an area of 6. This is an area of 3 times 3 over 2. So that is 4.5. And then we're going to add these together, and that we get 10.5 meters per second, which is D. Good. Okay, so 2, a child left her home and started walking at a constant velocity. After a time, she stopped for a while, then continued on with a velocity greater than what she originally had. All of a sudden, she turned around and walked very quickly home. Which of the following as our distance versus time graphs? She doesn't go backwards when she stops. So that's kind of what we have in almost all of these cases. They have her stopping, then they have her turning around. But after she stops, she continues on with a velocity greater than she already had. That's only accounted for in this one. This would be B. Because she starts out with a velocity, that's what we've got here. She stops, that's this time here. Continues with a greater velocity, that's this part, moving at a steeper angle. Then turns around and goes home quickly. And that's when she actually changes directions and we start going back down. These little parts where we go back down earlier are not accounted for in the story. So we don't want any of those options. So yeah, we're just going to stick to this one. Cool. We've got a wiffle ball is tossed straight up, reaches the highest point, and falls back down. Air resistance is not negligible. So what do we know? Which of the following statements is true? The ball's speed is 0 at its highest point. If it's tossed straight up, that is going to be true because there's going to be no horizontal velocity to give it speed. Speed would be the magnitude of our velocity. So if we're going sideways, but our vertical velocity cancels out, we still have speed. So 1 is true. I'm just going to circle the things that are true here, but then we have to pick a choice. The ball's acceleration is 0 at this highest point. That's not true because we're going to be accelerating due to gravity constantly. But we also are going to be experiencing some air resistance acceleration also. Either way, not 0. Because if the acceleration was 0 at this highest point, it would just stay there. It would just stay at rest, floating up there like some magic wiffle ball. The ball takes a longer time to travel up to the highest point than to fall back down. So this is an air resistance problem. And so we expect air resistance to be opposing us as we travel. I think technically this is going to go 3 is technically going to go be true because, and it's really depending on how they interpret this. But if we define our air resistance, let's get us a new page here. So our ball is traveling up and then it's traveling back down, right? In this upwards velocity though, we have our highest velocity is at this point. And for our second one, our lowest velocity, our highest velocity is at this lowest point. Now air resistance, we'll call F drag, goes something like, it depends on our velocity, right? So when we have our high velocity, we're immediately experiencing strong air resistance right off the bat. At the top, there's we're at rest, and then we kind of, as we start to fall, then our velocity never really gets a chance to build up as much as when we had that initial launch. So because we're being constantly held back by the same drag force, so then the magnitude of this drag force never quite reaches the level that it did down here. And so I would actually then assume that we have... No, it's still symmetrical though. I mean, it would still reach that. Yeah, I think that the symmetry is going to win out here. So I think that's going to make this not true. That is a tricky one though. And that's one I'm not wildly confident on. We'll keep an eye on that one. Maybe that's one that we're not correct on. We can check that later too. Above we have a graph for distance versus time of a car moving along a road. So that's distance versus time. Which of the following times would the automobile have been accelerating positively? So that means positive acceleration means that we are increasing at an increasing rate. So this would be one example, right? Our slope is getting steeper and steeper. So from 0 to less than 10 minutes. So I guess 5. And then up here, we're accelerating positively because we're going this way. So that's right around 30 minutes, or 29, I guess. And then this last time is a little bit serendipitous because, I mean, it shows up in our answer that we want because we can already rule out 12, and this one doesn't have 5. So this is our best answer right off the bat. But this positive acceleration isn't putting us in the positive direction, but we're moving in the negative direction. So this is a deceleration of a negative velocity, which means a positive acceleration, because acceleration is the rate of change of velocity. Good. We've got a large beach ball is dropped from the ceiling of a school gymnasium to the floor about 10 meters below. Which of the following would best represent its velocity as a function of time? Do not neglect air resistance. Okay, so if we were, I know we said not to, but if we were to neglect air resistance, we would expect a straight line like this, right? Not this flat part, but we would just expect a constantly increasing velocity. However, as our velocity gets higher and higher, we're getting more force pushing us, so that would be pushing upwards. If it is falling down, the drag force is going to oppose our motion, so that's going to be pushing up. Either way, it's reducing our velocity, and so we're increasing at a decreasing rate, which would be C. As V gets higher, the force against it gets stronger. And that's what we saw earlier with that drag force. Check on the stream here. How are we doing? Still no viewers. Okay, I think I'll cap this at about an hour. We'll call this a test of technology. Oh, and now I opened Opera. I don't want that. Opera, go away. Ah. Okay, back to our problems though. Okay, so we can do a couple more here. We got a car starts from rest, accelerates as shown in the graph below. Okay, so this is our acceleration as a function of time. What time would the car be moving with the greatest velocity? So that's going to be here at time 4. Oh, I didn't want to draw a picture like that. Yeah, you know, screw it. Let's draw our picture. We've got time. So here's our acceleration, and it's moving something like, we got a positive peak and a negative peak. And I remember this was 4 seconds. I don't remember the other stuff, but that's our A, that's our T. And so our velocity is going to be our area under the curve, right? And so for this positive part, up until 4 seconds, even though our rate of acceleration is decreasing, it's still a positive acceleration. So we're still positively increasing our velocity. Until here, our acceleration changes direction. Then after this time, we're now reducing our velocity. We're accelerating it in the opposite direction, and so that's going to be slower. So our maximum velocity is at that time 4. What time would the car be farthest from its original starting position? Well, that's actually going to be all the way over, because even though our velocity is now getting reduced on this other side, but it's still positive, right? Until we get all the way out to 8, when we come to rest, our velocity is still taking us in the positive direction. And so that's going to be 8 seconds then for our most positive. Which of the following sets of graphs might be the corresponding graphs to the position, velocity, acceleration of a moving particle? Okay, so we're just comparing a full set of 3 graphs to see if they all correspond with each other. So right away we can throw out A and B because they have the wrong relationships between acceleration and velocity. We expect if acceleration to be flat, velocity to be curved, to be an angle like that. And immediately then D messes that up. So we're left with C. So C is our best option just by looking at all the other ones and seeing where they're wrong. But we can also just take a look and see, okay, we're increasing at a decreasing rate. So I expect a positive velocity that is decreasing. That's what we have. And our velocity is decreasing at a constant rate. So I expect a negative constant, which is what we have. So C checks out even regardless of looking at the other options. Next we have an object is thrown with a fixed initial speed, v0, at angles alpha relative to the horizon. At some constant height above the launch point, the speed v of the object is measured as a function of the initial angle alpha. Okay. Which of the following best describes the dependence of v on alpha? So that's going to be speed. So it actually is not going to affect us. No, it's okay. No, it's not, because we'll have some constant height. So our initial speed, our total speed, we have as we shift our function with this alpha, we're determining how much of our v is going into our vertical component and how much is going into our horizontal component. That being said, we're splitting this up like that. We can split it with a sine and a cosine. When we take the how do we want to put this? Well, when we take this back into speed afterwards, because we're still looking for the final dependence of our speed v, even though it says v, it's not a velocity. Speed is going to be the magnitude of our velocity, which takes into account both components. We can take a look at this mathematically, what this would look like if we look at our speed as 2 components, right? So we'll call this v, we'll call this vx, and we'll call this vy. I'm going to take a quick peek at this thing just because I know it's Swiper's birthday. Nope, That's okay. I didn't expect anything. Anyway, so our y component, if this is our angle alpha that we're dealing with, right? And so our y component is then going to be the sine of this angle times v sine alpha. And similarly, our x component is going to be v cosine alpha. But then when we go back to find our new v, we'll say, well, that is equal to the magnitude of vy squared plus vx squared, which when we take that together is going to be, in parentheses, v sine of alpha squared plus v cosine of alpha squared. And so we can pull a v squared out from this and say this is the square root of v squared times sine of alpha squared. Let's put squared there, actually. Sine squared of alpha plus cosine squared of alpha. And this is a trig identity. Sine squared plus cosine squared equals 1. And so really, our v is just equal to the square root of v squared, which is v. So, but we see this has no alpha dependence. And so what that means in the context of our problem is v will remain constant independent of alpha. By changing this angle, I know we're measuring different components. If we assume that the height is achieved and there's no air resistance, it's not going to make a difference. Position versus time graph for an object moving in a straight line shown below. What is the instantaneous velocity at t equals 2? It's just going to be rate of change. We've got a flat slope. We go from 4 to 0 in 2 seconds, so it's going to be a rate of -2. And it's the same line, so it's still going to be a, -2. Good. Nice, quick, easy one. Shown below is velocity versus time graph for a toy car moving along a straight line. What is the maximum displacement for the toy car? That's going to be this area under the curve. So we've got okay, so we've got 1.5. So half a second times 4. Let's draw this and add this up. Okay. So we've got, here's our v. There's our t. Our maximum displacement is going to be before it crosses 0. We've got something kind of like this. It's not drawn to scale. Let's have a look at it. Oh, it's much wider than I drew. This is more like that. Yeah, let's do that instead. Okay, so what we can do is we can break this into regions. We can break this all into little areas that we can add up. We got a triangle, we got a second triangle, and 2 rectangles. Well, let's do the rectangles first, just because they're going to be easy. First one, we've got a width of 1 second, a height of 2. So that's going to give us an area of 2. This one's got a height of 4 and a width of 1/2. So that's also going to give us an area of 2. That's 1/2 times 4. This top little guy, what have we got? We've got a height of 2, width of 1, and then we're going to divide that by 2 to get us the area of a triangle, which gives us 1. And then this last guy, oh, that's the wrong button. Where's my problem? There it is. Last guy, we're going from 1/2 to 2.5, so it's a width of 1, height of 4, and then divide by 2. That's going to give us an area of 2. So adding these all up, I get my total x displacement is equal to 7 meters, I guess. Which is C here. Cool. Got an object falls from rest, released from rest, falls different distance h during the first second of time. How far will it fall during the next second of time? So yeah, we can relate our distance to time with our, sorry, I'm trying to find the right tab here. Yeah, I could really uncomplicate this setup in the future. The distance we travel, which actually we might as well use as a y, because we are falling. This y distance that we are traveling is going to be equivalent to our constant acceleration times our time squared. So for our first case was after 1 second, we said that 1/2 a1 squared, so at squared, which is really just a over 2, they said that that was h. And so now we want to look at what happens when t equals 2 for the next second. How far do we travel? And so we'll just take our position at t equals 2, and then we'll minus this original position to see how much we traveled in that second. In that deuxième second. Ugh, that's weird. And so that's going to be, let's do this over here. Y equals 1/2 times 2 squared, which gives us a 4 on top. And so we now have our y is equal to 2a, which if we compare to this guy, 2h was equal to a. So our y position after our second is 4h. So that means in the second we've traveled, in that next second of time, we've traveled 3h. We ended up on 4h, but we got that first distance from the first second. So this is how much we got from the second one. I think this might be my last one for tonight. Let's have, is anyone watching? Yeah, I think this will be my last one for tonight, and then we will wrap this up. This has mostly been a test of the tech. I've learned a lot about how I want to lay this out better. If I can get this in a way where I can read the problems and write at the same time, we will be in a really good position. And so we have 2 identical bowling balls dropped from rest at the top of a tall tower shown in the diagram below. Okay, so they've got different head starts. Ball A is dropped 1 second before ball B, but both fall for the same time before ball A strikes the ground. Air resistance is negligible after ball B is dropped, but before ball A strikes the ground. Which of the following is true? Okay, so I was confused by that sentence. The distance, so before A strikes the ground, but after B is dropped, the distance increases. That is one of the things that is going to be true. Oh, decreases is not true. We expect it to increase. The velocity of ball A in respect to ball B is increasing. This is the rate of increases. So they're both increasing at the same rate. A has a higher starting velocity, but they're increasing at the same gravitational weights. So they should have, ball A's velocity is not increasing with respect to ball B. The distance apart is going to be increasing because ball A is traveling at a higher velocity than ball B. So I guess we'll call that D. D is our best option here. C and B kind of are talking about irrelevant ideas. Well, not irrelevant, but ones that aren't actually going to be affected by the same gravitational field. And A is the opposite of D, so A cannot be correct. Good. Well, I think that I'm happy to call that here. This was just kind of a test of kind of a tech demo to see what we could do, how easily it was for me to write and read problems at the same time. Turns out it's difficult if I can't see the problems at the same time, but I like this idea of keeping all this stuff together. I think also I might, maybe not right now, but I might move this in a way so I can look at the camera without having to like check back over here, something like that. But for everyone who tuned in, I appreciate it. Oh, I also couldn't see the bottom there. That's something else I need to... Oh, no, never mind. That's fine. So, until the next time, though, everybody, you take care, stay safe, and I'll see you on the next one.